All right, so on the screen right now are a series of equations that I strongly encourage you to write on the back of your packet called In-Class Energy that you picked up on the way in, or it's posted on Canvas under today's agenda. Let me show you really quick where that is. Sorry for you people who are copying these down right now. We'll come back to it in a second. Actually, gotta push the right button. So under today's modules, in-person agenda, here's that packet in-class energy, and then here are the equations that I have up on the screen. So I'm going to kind of be referencing these as we go, but that's where we are getting these equations from. So a couple of these, most of these, almost all of these, let me rephrase that. Almost all of these equations I introduced to you on Monday. This was our very generic equation dealing with work. Work is plus or minus some parallel force times the displacement. There were 4 types of works we specifically dealt with, and those types of works were very specific to the force that we looked at. And I said there were 4, and I said after yesterday, your virtual day, we're only going to care about 2 of them. And these are the only 2 I really care about anymore. Is my work in and the work done by friction. The work done by the normal force was kind of a silly one because for us, because we don't deal with inclined planes, it was always going to be 0. The work done by gravity is definitely an important one. However, we can get to it using potential gravitational energy, and we will address that, but it comes from the PEG piece of it. So in terms of this general equation is used to derive these 2 equations. These are important. I defined the 3 types of energy. Work is when you expend energy to do something, and work causes a change in energy. And I introduced on Monday the types of energies that might change. We didn't do anything with the energies. That's going to be what we're talking about today. But the 3 types of energy are kinetic energy, gravitational potential energy, and potential elastic energy. And those were written, I'm going to switch on Monday's worksheet. We wrote those like on the side column. So the definitions with what each variable represents are all written here. In addition, that is posted on Monday's in-person agenda, pictures on the bottom of that. So if you didn't get that, those pictures are posted there as well. So types of energy. There's 3 types of what we refer to as mechanical energy. So we are dealing with mechanical energy, and it's kinetic energy, gravitational potential energy, and potential elastic energy. 1/2 mv squared and mgh 1/2 kx squared. We aren't going to deal with PEE today. We'll do that Monday. So today we're really going to be focusing on these 2. Now, what this equation is, ME, I don't have it written anywhere, I'm telling you verbally, ME simply stands for mechanical energy. ME stands for mechanical energy. So some of our early questions will be asked is how much mechanical energy does an object have? And when I say how much mechanical energy does an object have, I'm asking how much kinetic and how much gravitational potential energy and how much potential elastic energy does that object have? Because it's moving, because there's a height, or is there a spring? So I calculate this number, I calculate this number, I calculate this number, and I add those 3 numbers together. If I ask you for mechanical energy, ME is we take those 3 types of energies and I add them together. Very conveniently, a lot of times 1 or more will cancel out. It's not moving, or it doesn't have a height, or there is no compressed spring. Sometimes, not always. Okay? So as we kind of keep working down the list, these are the 3 types of energy. Collectively, they're referred to as mechanical energy. These are 3 forms of mechanical energy. There's lots of other types of energy in the world. There's sound energy, there's heat energy, there's nuclear energy, there's intermolecular forces, intermolecular forces. There's other types of energy, okay? we are dealing with what we refer to as mechanical energy. This is sometimes, this equation right here is the part in the red. That's the equation. The equation in red is the equation. And what this equation is, it's a combination of work in plus work done by friction, work in, work done by friction, is equal to our change in mechanical energy. So just like in chemistry when they talked about a change in temperature, or we talked about a change in position, it's your final minus your initial. So when we talk about ME2, or change in mechanical energy, so that's what change in ME means, is we're talking about change in mechanical energy. We're saying my mechanical energy at location 2, my final location, minus my mechanical energy at my first location. Now, how do we calculate mechanical energy at location 2? We find the kinetic energy at location 2, the gravitational potential energy at location 2, and the potential elastic energy at location 2, and we add those three things together. And then we subtract change in my mechanical energy at location 1, which is KE1, PEG1, PEE1. So when this equation is fully expanded, it's long. There's 6 different variables because this becomes this, and then this becomes this minus this. It's long. For lack of creativity, we sometimes refer to it as the long equation. It's the work in equation. Now, I'm trying to, this thing on the side, I'm trying to give you some hints and some suggestions on when you use what. So when we start dealing with energy, there are certain questions that will talk about a single location. And a single location problem, one location problem, a typical question will be how much mechanical energy does an object have here or at this location? And if I'm asking how much mechanical energy does it have at a location, I'm asking you to take and solve this equation for ME. So how much energy does it have because it's moving? How much energy does it have because there's a height? And how much energy does it have because there's a compressed spring? Sometimes those things are zero. It might not be moving. There might not be a compressed spring. It might not have a height. And by asking these questions, we can kind of go through and say, is it moving? No. No kinetic energy. Is there a height? No. Then there is no gravitational potential energy. Is there a compressed spring? Yes. Okay. Then there's PEE. Sometimes there's 2. Sometimes there's all 3. And then it's plugging in the numbers in your equation and solve it. That's how we're going to start. Then, when we get into what we are often comparing 2 locations. When we compare 2 locations, then we use the long equation. That's when we use the work in plus the work done by friction is equal to change in mechanical energy. Now, there's a very convenient thing that we're going to do with that long equation, and we're going to start off with. We're very conveniently going to have situations where there is no work in and there is no work done by friction. And then that situation is a special type of that problem. It's called the conservation of mechanical energy problem. And we'll deal with all those. So lots of equations. Today, what we're really kind of focusing on is like right in here with a little bit of this, but a very special type of that problem. So we got a really big packet. I don't even know, 6, 7 pages long. It's really long. We aren't going to do it all. So don't think we are. We will work on a little bit more of this on Monday. Okay, but these are general equations, and these are the equations that I'm going to be referencing throughout. So I'm probably not going to keep this up. I might be kind of flopping back and forth between it. On the video, I probably will put it back on the screen, but I won't pan over it for you to see it. So I'll write them on the board as I work through these problems. Okay, so where is All right, so what we're gonna do is we're gonna go through a couple of these problems together. Actually, a fair amount of these problems together. And I'm gonna try to show you how to do these problems. Oops, sorry, video land, I should have started here. Okay, we're gonna start with number one. We're gonna do number one together. Then I'm gonna have you try number two. Then we're gonna, so that's kind of the idea of the circle versus underline. Okay, so when we go through and we look at problem number one says how much energy does, and pictures are gonna be good. How much energy, doesn't say mechanical energy, I think I fixed that on your homework sheet so they do, and on your test, I'm pretty sure I fixed it so they do, but I'm asking how much mechanical energy, problem number one, does a 15 kilogram block have that's traveling 15 meters per second? Pictures I think are pretty good. It doesn't tell us whether that block's moving vertically or horizontally because it doesn't say it's falling. I'm gonna go with it's moving horizontally. It talks about an object moving with a velocity of 15 meters per second, and it has a mass of 15 kilograms. It is talking about one object at one location. Okay, it's talking about one object at one location. How much mechanical energy, how much mechanical energy does it have at a location? We are using this equation. We are going to use, because it's a one location problem, and it's asking how much energy, how much mechanical energy, I'm asking how much kinetic energy does that object have, and how much gravitational potential energy does that object have, and how much potential elastic energy does that object have. I'm asking all three of those energies added together. I referenced on Monday the questions that I'm going to ask you. I'm going to refer to the questions that you ask. These are the questions, I wrote them in blue I think on Monday on your sheet, they're up there in black. These are the questions that we ask ourselves for the different types of energy. And by asking these, what I consider relatively simple questions, really help us identify what types of energy exist at that one location. So if we look at our question for kinetic energy, is the object moving? Does the object have some type of velocity? Because I drew a picture, we could say, yeah, look, there's a velocity. Is it moving? Yes. Underline if you want, don't underline with it, I don't really care. But yes, it is gonna have kinetic energy. Does that object have some height? That's PEG. Is there a height? No, right? Or you could say, well, it's off the floor, yeah, that's 2.5 meters. But yeah, it's 1.5 meters here, and 1.5 meters here, and 1.5 meters. So really more than just, is there a height? Are we changing height? That's really kind of what we're referencing. More when we get to the two location problems. But at this type, is there a height? The answer is no, there's no height. Therefore, there is no gravitational potential energy. Is there a compressed spring? PEE, is there a compressed spring? Now remember, a compressed spring could be a stretch spring, rubber band, bungee cord, or compressed or stretched, doesn't matter. And no, there's no springs, and just so you know, we aren't going to deal with any springs today or in your homework tomorrow. So there is going to be no PEE till Monday. All of my mechanical energy is in the form of kinetic energy. So what I'm asking you, I should have probably put this, I'm asking you to solve for mechanical energy. And so ME is equal to kinetic energy. How do we determine kinetic energy? Well, we use the formula for kinetic energy, which is 1/2 times the mass of that object times the velocity of that object squared. So the mass of my object, kilograms, knowing units is still important. Mass is measured in kilograms, so 0.5 times the mass of 15 times the velocity of 15, but it's 1/2 mv squared. The v is squared and only the v is squared. What we get for a final answer is we get a mechanical energy of 1,687.5 How much mechanical energy does this object have? It has, assuming I did my calculation right, 1,687.5 joules worth of energy. In this particular problem, all of the mechanical energy comes from the fact that it's moving, the fact that it has kinetic energy. Okay? I want you to try the second one. How much energy, how much mechanical energy does a 2.4 kilogram ball have that is 4.2 meters above the, oops, sorry, that's number 4. Number 2, how much energy does a 2.5 kilogram block have that is traveling at 25 meters per second? I will draw a picture. It's a one location problem. It's asking how much mechanical energy does the object have. Can I erase this? Am I okay erasing this? This is how we set it up. It's a ME equals question mark. It's a one location problem. Because it's a one location problem and we're trying to solve for ME, mechanical energy is KE plus PEG plus PEE. Drew a picture, I just quickly modified my previous one. And then you go through and ask yourselves the questions. Is it moving? Is there a height? Is there a compressed spring? Pause for a little bit just to give you a bit more time in case you need it. So when we go through and ask ourselves, is it moving? Is there a height? Is there a compressed spring? Is it moving? Mm-hmm. Yes or no? Mm-hmm. Yes. Is there a height? No. Is there a compressed spring? No. So all the mechanical energy is in the form of kinetic energy, and the equation we use for kinetic energy is 1/2 times m times v squared. Where does that come from? It came from the equation that I had listed on the screen that says Ke equals 1/2 mv squared. From there, we're plugging in numbers. Mass of 2.5 times 25 squared. Our mechanical energy at that location, I get to be 781.25, and our units are joules. Mechanical energy is measured in joules, work is measured in joules, all types of energy are measured in joules. Questions? All right, let's try the next one. Number 3, we'll do this one together. How much energy, how much mechanical energy, single location, does a 5.6 kilogram ball have that is 3.5 meters above the ground? 5.6 kilogram ball have that is 3.5 meters above the ground. How much mechanical energy, I'm substituting the word mechanical because it should have been there. How much energy, how much mechanical energy does that ball have when it's 3.5 meters off the ground? It's a single location problem. So because it's a single location problem, it's an ME equals question mark. How do we determine mechanical energy? We use the equation from the screen, it's not up there right now, that says ME is equal to KE plus PEG plus PEE. And some of you are like, do I really need to list all 3? I think you should. I think it's a good step. It should help us down the road. Now we ask ourselves the questions. Kinetic energy, is it moving? Does it say it's moving? No. Therefore, no kinetic energy. Is there a height for PEG? Is there a height? Yeah, so H is equal to 3.5. Yes. Is there a compressed spring? No. So all my mechanical energy, single location problem, is because of PEG. How do we calculate PEG? Our formula for PEG is M times G times H. There's multiplication in between those. The mass of my ball is 5.6 kilograms. The gravitational acceleration, we're on Earth, unless I tell you otherwise, we are on Earth, is 9.8 meters per second squared. The height, 3.5 meters off the ground, my height is 3.5. .6 times 9.8 times 3.5. I get the value, my total mechanical energy at that one location is 192.08 joules, assuming I did my math right. You try number 4. How much energy does a 2.4 kilogram ball have that is 4.2 meters above the table? Single location, how much mechanical energy, how much kinetic, and how much gravitational, and how much potential elastic. So, my quick calculation, drew a picture, mass is 2.4 kilograms, height is 4.2, doesn't say it's moving, doesn't talk about a compressed spring, talks about single location, how much energy, how much mechanical energy, so how much is kinetic and gravitational and potential elastic. Is it moving? No. Is there a height? Yep. Is there a compressed spring? No. PEG, M times G times H, I get 98.78. I don't know why I put 3 decimals. Don't tend to do that. Questions on that? So in these 4 problems, all the energy was in one form. It was either all in gravitational potential energy or is all in kinetic energy. Yes, but that's not always the case. So if we take a look at number 5, number 5 says, how much energy does a 2.5 kilogram ball have that has a height of 2.5 meters that is falling at 3 meters per second? How much mechanical energy, how much mechanical energy, single location problem, does an object, a ball, I don't even know what it says, a ball, 2.5 kilograms. It has a height, h is equal to 2.5 meters and is falling at, is moving, it has a velocity of 3 meters per second. How much mechanical energy does that object have? Single location, right? We're only talking, how much energy does it have at that one point? So how much mechanical energy, how much kinetic and potential gravitational potential energy and elastic potential energy does this object have? Ask ourselves the questions. Is it moving? Yes. That's KE. PEG, is there a height? Yes. Is there a compressed spring? No. Okay? Identifying types, that's key. Then calculation, mechanical energy is equal to, instead of saying KE, we can write KE as 1/2 times m times my velocity squared. We'll switch colors as I show you. There's a plus sign right there. Plus, my formula for PEG is m times g times h. Now, mathematically, order of operations say we have to do the multiplication first before we add those two numbers together. Just so we're clear on that. You can't take v squared and add it to m and then do the other stuff. That's not how math works. So, ME, 1/2 of the mass, 2.5, times the velocity of 3. Don't forget to square it. Be surprised how many times people drop that squared. Plus 2.5 times 9.8 times the h of 2.5. My mechanical energy is equal to 11.25 plus, that's only the kinetic energy piece, 0.5 times 0.5 times 3 squared. My gravitational potential energy piece is 61.25. So how much total mechanical energy do we have? Well, we add those two numbers together. And we get a value of 72.5 joules. 72.5 joules. This mechanical energy has two types of energy. It has kinetic and gravitation. Why don't you try number 6? How much energy does a 5.2 kilogram ball have that has a height of 12.5 meters and is falling at 3.5 meters per second? Again, units of meters is important, units of meters per second, kilograms, those tell us things. I got a number of 668.85 joules. And I went through and did. There's gravitational potential energy, because there's a height, m times g times h, m 5.2 times 9.8 times 12.5. There's kinetic energy, 1/2 mv squared, so 1/2 times 5.2 times 3.5 squared, and then we have to add those two numbers together. We good, or do I need to work that one? You want me to work that one onto the board? Good? Okay. That's if it's a one location problem. I'm going to say, I hope that you all find one location problems pretty straightforward. But that one location problem is an important step to get us to the two location pieces. So when we start talking about two location problems, I really encourage pictures. When we start comparing two different locations, then we use a much longer equation. We use that work in plus work done by friction is equal to our change in mechanical energy. And the change in mechanical energy is ME2 minus ME1, and then we can keep expanding that out too. Early on, we have this special condition that sometimes is met, and it's called conservation of mechanical energy, and we'll express that. So we have a skier, 50 kilogram skier, starts at the top of a 100-meter high hill, just so that for the record, that's about 300 feet tall, not super tall if you're a skier, and it skis down the hill. With what speed will that skier be going at the bottom of the hill if friction is neglected? Very convenient that there's no friction. Complicates things a lot. Okay, but we have a skier. They have a lot of, what's that word? Camber? Really curved. I don't remember what that term is called. Gotta wear a helmet, of course. And a neck gaiter. You're at the hill and it's COVID. Okay, so we are a skier on the hill. The hill is 100 meters tall. The skier has a mass of 50 kilograms. Because I'm an amazing artist, I didn't actually have a block to put his mass in, but maybe a block would have been better, because then we get to run the mass in there, but whatever. The skier starts at the top of the hill, 100 meters high, and skis down the hill. With what speed will we be going at the bottom of the hill if friction is neglected? So why is it a two location problem? Because he starts at the top of the hill, I'm going to call that location number 1, and he ends at the bottom of the hill. I'm going to call that location number 2. Because there is a height, a change in height, I find it most convenient if we define the lowest point to have a height of 0. We don't have to. We could define this to be 0 if we wanted to, but then this has a negative height, which would be perfectly okay. But we're looking for some things. Now, just to kind of be upfront, when we look for things, we are looking for mass, we are looking for velocities, we're looking for heights, and that's spring stuff, but we don't have any spring stuff. But when we look at velocities, we're looking for a velocity 1 and we are looking for a velocity 2. Velocity at location 1, and we're looking for a velocity at location 2. We're looking for a height at location 1, and we're looking for a height at location 2. Okay, so we're comparing those two heights. Mass isn't going to change, just for the record, I know that. So, we are looking for V1, we're looking for H1, we're looking for V2s, we're looking for H2s. And the more of this we put on our picture, the better off feel we're going to be. So, if we define the lowest point of the hill to be 0, and if the skier is at the bottom of the hill, the height of the skier at location 2 is 0, right? He's at the bottom of the hill. He can't go down any further. If this is 0, then from here to here, my H1 is going to be 100. How fast are they going at the bottom of the hill? My V2, that's our question mark. That's what I'm asking you to solve for. And we're left with V1. Now, V1 is not stated. It says a skier starts at the top of the hill. Hopefully that's implied enough for you that he is at the top of the hill and he's going to start. Hopefully we're clear he's not moving at the top of the hill. Now, is that always the case? If you ever go to Granite Peak, I feel like there's an awful lot of people that go to the top of the hill and then just stop and then look over the hill and then go, which is fine if you're learning, that's fine. Because you want to know what you're heading into. If you're a more experienced skier, you kind of got to dodge those people then, but it's okay, you can do it. But we're at the top of the hill, so we're going to say, hey, let's do it. Now this is where that really long equation starts. It's a two-location problem. So because it's a two-location problem, we can say the work in plus the work done by friction is equal to our change in mechanical energy. I'm going to do one more line before I start canceling some stuff. I'm going to say work in plus work done by friction is equal to change in mechanical energy. What that change in mechanical energy means is what is my mechanical energy at the end? How much mechanical energy do we have at location 2? That's exactly what we just did 6 times. We found the mechanical energy at a location, right? That's ME2. And then we have to subtract that from how much mechanical energy does that person start with. That's exactly what we did 6 times. How much mechanical energy does this skier have at this one location? That's ME1. But now we're comparing the 2 locations. That can be further expanded, and we'll do that in a second. I want to draw your attention to the work in equation and the work done by friction equation. Work in exists when there's an applied force. Work done by friction occurs when there's a force of friction. That's what the equations say. Applied force, force of friction. In this problem, so questions to ask ourselves. For work in, is there an applied force? And if so, is it move, right? Because I can apply a force, but if the board doesn't move, I don't do work. I didn't do any putting work in. So let's just start. Is there an applied force? And then is there friction? And if the answer to is there an applied force is no, we can cross that off. If the answer is yes, we have to keep it. Is there friction? If the answer is no, we can cross that off. If the answer is yes, we got to keep it. So what are the answers to those questions? In this problem, does it talk about the skier pushes off with their poles, or they push off with their skis, or their friends give them a push? No. No. So is there an applied force? No. There's no applied force. Is there friction?
No.
Friction is neglected. Very convenient, by the way. What work in does is it adds energy to the system. What friction does is it removes energy from the system. So what this is saying is I'm not gaining any energy, I'm not losing any energy. We do a quick mathematical switch. If I add ME1 to both sides, what we get is we get a new equation that says ME1 equals ME2. This ME1 equals ME2 is a special variation of this equation that is referred to as the conservation of mechanical energy. Conservation of mechanical energy. And conservation of mechanical energy only exists if there's 2 conditions that need to be met. There's no work in, and there's no work done by friction. I will do these steps for a while. At some point, we're hopefully going to be like, is this a conservation of mechanical energy? Yes, because there's no work in, no work done by friction, and then we can go ME1 equals ME2. But that's kind of where we got to get to. There are going to be some problems where, yeah, down the road next week, there is going to be work in. There is going to be work done by friction. And then we got to deal with those at that point. But this special type of mechanical energy, or special type of 2-location problem, is called conservation of mechanical energy. And ME1, all my mechanical energy here is equal to all my mechanical energy here if this is 0 and this is 0. So how do we solve this? Well, remember, mechanical energy is Ke plus PEG plus PEE. Now we're talking about mechanical energy at location 1, so we go 1, 1, 1. That's ME1. And we set that equal to ME2, which mechanical energy is when we take our kinetic and our gravitational potential energy and our potential elastic energy at location 2 and 2 and 2, and we add those things together. Still, this looks like a really long, pretty long equation. Yeah. But we can get rid of a lot of it. Because we can go back to those questions and say, what's the question for kinetic energy? Is it moving? Now we got to be careful. Is it moving at location number 1? No. At location number 1. See how I wrote that out? It's very purposely trying to draw your attention to, is there a V, is there an H? Is there a V, is there an H? So, is there, I wrote it my face with a marker. Is it moving at location 1? No, it is not moving at location 1. Therefore, there is no kinetic energy at location 1. Is there a height at location 1, right? This is my height. This is my H1 right here. From here, I wrote it there too, but sorry. Is there a height? Yeah. So there is PEG at location 1. Is there a compressed spring at location number 1? No, no compressed spring. Now at location number 2. Is it moving at location 2? Yeah, this is what we're solving for. Yes. Even if that number is 0, we have to solve for that in the KE. So is it moving? Probably. Go down a hill on skis, you're probably going to be moving at the bottom of the hill, especially if it's the first hill on this hill. But yeah, okay, so yes, we got to keep that one. Because we chose the height of this to be 0, the bottom of the hill to be 0, conveniently, that is also going to be 0. I don't know why I put a 0 above that. I didn't put a 0 above anything else across that. And is there a compressed spring? The answer is no. Now, if you didn't choose this to be 0, it'd be okay. If you would have said this was like 100, then you have an H2. It's 100. But if H2 is 100, that means H1 is 200. So you'd have an H1 and an H2. It works out. How do we find PEG? Well, our formula for PEG is M times G times H. And I'm talking about PEG1, so therefore I'm talking about H1. I don't have to talk about mass at location 1. Assuming he doesn't lose a limb along the way, he's going to have the same mass. We don't have to talk about gravitational acceleration at location 1 versus 2 because it's Earth. So we really only have to clarify that it's height. And we can set that equal to KE2, which our KE equation is 1/2 times the mass of the skier times the velocity of the skier at location 2, and we need to square that. Now, mathematically, can we simplify this any? Could this equation get simplified mathematically at this point? Yes. There's something that can be canceled. What could be canceled in this? The mass. Because there is a mass in every term. There's only one term on each side. But because there's a mass in every term on both sides of the equation, we can, in fact, cancel out a mass. If you do not feel comfortable with that cancellation, don't. Leave the mass of 50 kilograms in. It will make no difference. But it is acceptable to cancel the mass because there is a mass in every term on both sides of the equation. Plugging in numbers at this point, G has a value of 9.8. My H1 is 100, which is equal to 1/2 V2 squared. 9.8 times 100 is 980, which is equal to 1/2 V2 squared. Divide both sides by 1/2, which really means we double that. I believe is 1,960. Is that correct? Okay. Then we have to take the square root. Don't forget to take the square root. Some people like to try to take the square root here, which is possible, but almost everyone that does that screws the algebra up, so I don't recommend it. So the square root of 1,960 is plus or minus, but we're going down a hill, so V2 is equal to 44.27 meters per second, which, for the record, is crazy, silly fast. You should never go that fast on a pair of skis. 44.3 meters per second in miles per hour. 99 miles per hour. Do not recommend going 99 miles per hour on a pair of skis.
Would be kind of sick.
Kind of fast.
Yeah, well.
Okay, so we didn't get as far as I kind of wanted, but that's hopefully going to be okay. Okay, now you do have a homework assignment somewhere. There it is. Your homework assignment starts off with the one location problems like we just did. I'll put some here and I'll put some here. They quickly move on to two location problems. There are 3 two-location problems. When you do a two-location problem, you set it up like this. I will, after school tonight, I think, yes, I will. After school tonight, I will record a video going through page 3, problem number 1, on the top of page 3. Because on the packet, from the packet. Okay, because question number 8 is dealing with springs, we are doing springs. I will work through problem number, the one on the top of page 3, and I will record that video, and I will post it to Canvas. So if you get to a two-location problem and you're like, how do we do that? I would encourage you to log into Campus. I'll post it under, should I post it under the assignment or in the in-person agenda? Probably the assignment. Post video in the assignment link. I'll put it there. Okay? Have a great day. Have a great weekend.